gradients.
But you either need gradients or really large number of microformations because that's what the next
The problem is that you don't know which direction is downhill. That's all it is. There's too many dimensions for a single proposal in one dimension to be likely to go downhill. That's all. And so the gradient tells you which way is downhill.
I see. So that would just solve it. You could do
Yeah,
any number of dimensions at that point.
Well, I mean, we still have the curse of dimensionality, but it at least avoids the problem of not knowing which way downhill is.
Okay, thanks.
So I'm going to talk about stuff actually Jane and I are writing up right now that I'm excited about. So Jane is, speaking of gradients, developed code to compute gradients of things that you compute with simulations with respect to force field parameters. And we put a paper out about that, doing a very limited adjustment of like a couple parameters in a host, and then Jane got ambitious and said, let's play around with the water model. So I thought I'd tell you what happened with that. And I think it sets the stage for hopefully what Katie's doing. So basically, what Jane did is to start out with the TIP3P water model as a baseline. And so this is really a derivative of TIP3P. And set out to just modify the Letta-Jones parameters of that one oxygen. So it's just two parameters, but it has large ramifications since it's the water model and everything's happening in water. And all of the training and testing here, or most of it, is being done on host guest data. The total data set that's used here is about 128 free energies or enthalpies. And I think that's kind of cool because it means that the data set's approaching what something meaningful in size, and Katie will talk about expanding that. So just as a baseline, the force field, other than using TIP3P or some modification of it, is as shown there. And the training set is just 6 cases. It's octa-acid, which is this hydrophobic cup with some solubilizing carboxylates around the rim, 2 views of it, with these 6 guests, which have charges and then aliphatic portion. And so she computed, so there's code now where you can post-process a trajectory and compute the gradient of your observable. So here's gradients of binding free energy. And binding free energy is actually particularly easy with respect to your sigma and your epsilon of the water Letta-Jones parameters. And so I don't put these up as being particularly interesting numbers, just there they are, they exist. And this is but when you put them together, you can get the partial derivative of the mean signed error with respect to each parameter. And then what you did, so you can basically make a 2-dimensional scan from that of the predicted error, root mean square error over your training set with respect to sigma and epsilon. And so, and you can see that the errors get low down here, they get high as you go this way, and there's this long sort of trough here, and TIP3P is over here. So I don't know exactly how you did the search, but Jane tried various combinations of sigma and epsilon that moved this in the right direction and computed pure water properties for those.
Wait, why is it at the edge of the basin instead of in the middle?
The bind.
Yeah.
Oh, because if you go into the middle, you wreck the pure water properties.
Oh, I see. So this is just looking at the RMSE for the
yes,
binding. Okay.
Yes. I mean, I think it could have been merged with the pure water derivatives, but we didn't do that. Yeah. So basically, by using that information and going back and forth with pure water simulations, right, he came up with slightly modified parameters. So here's the TIP3P sigma, here's the TIP3P epsilon. The charges stay the same, and here are the modified ones. And these are the pure water properties. So they're the densities. Basically, sigma gets a little bit smaller and epsilon gets a little bit larger. So you preserve the density, the dielectric constant is further overestimated, but not dramatically more. And these other properties are all pretty decent. The enthalpy of vaporization is still decent.
So TIP3P was parameterized with the 9 angstrom cutoff using Monte Carlo with no correction for dispersion or anything like that. So if you were just to use your modern protocol, which presumably uses PME, a dispersion correction, and all these other things, and an actual barostat, is it possible that liquid properties are actually, I mean, they're not any much worse, right? So
Well,
What-
she recomputed these. These aren't from the literature.
Sure,
So these are the same protocol.
Sure.
Oh, okay, sorry.
So they're pretty similar, right?
Oh, yes.
Which is, but so what is the basis of like good liquid properties look like? Is it just super flat everywhere, or
I don't
over
know.
this region?
I don't know.
or-
No, it'd be nice. It would really be nice to have this picture.
Yeah, for
the pure liquid
pure
properties. I agree. We don't have it.
Or I mean,
Right.
does your objective function? I guess if you go forward one more slide, does your objective function?
Is that
I guess they're both. Like some of them get a little bit better, like the isothermal compressibility, right? Gets a little bit better.
Yeah. I mean, if you think, I'm not sure how meaningful
Yeah.
the improvement it is, but
I don't know. I was just curious if this is this really being driven by the guest stuff, or is it being like you're just improving the liquid properties a little bit more to, by using PME and dispersion correction, for example, could you, if you omitted the host guest binding free energies, would you also get better parameters for
Oh, I see what you're saying.
It would be a different starting point.
I think it would. I think my impression is that the liquid properties are too degenerate
Yeah,
to
so
be
it's just too
useful
flat everywhere.
to be
Yeah,
useful to improve the host guest data.
got it.
Yeah, but I don't have data to back that up. That's an impression. So now I'm just going to show you a bunch of test sets. I'm going to show you what the water model does. Actually, why did I show you I don't have the training set data. Well, anyway, it improves the training set. I don't seem to put that in here. Let me just show you test sets, since that's what matters anyhow. So here we move up to the same host and a bunch of different guests that are maybe fairly similar in character. And this is experiment. Don't worry about this. This is the new model. This is TIP3P, and these are some other ones that we looked at for this particular set. Summary statistics are down here. Basically, going from TIP3P to this slightly modified version reduces the tendency to overestimate the binding free energies by about a kcal per mole. It's not dramatic, but it's in the right direction. The RMS error goes down a little bit also, but there's really no improvement in the correlation. There's no improvement in the scatter. And then what you're going to see is that's basically the pattern throughout all the test sets. That's what happens. If you compare with TIP4P, OPC, and TIP4D, which is the dispersion enhanced one from D. Shaw, which is used to prevent proteins from collapsing so much, you see actually this one is better, and I think it's maybe a little bit similar in flavor to what we've done, but maybe not quite as good.
Are these all in phosphate buffer?
What's the, remember, the buffer, the salt?
Yes, because the alkyl acid is negatively charged. So we only have sodium ions to neutralize the system, but no extra ions.
And this in your calculations, the sodium ions do compete for the small molecules. So that effect of like
I'm not sure how, that's in.
if there was
There
something
should be some
competing for the
competition, I guess.
host,
What's that?
if there was something competing for the host, the experimental numbers would all be smaller in magnitude than the calculated numbers. If
Oh,
you
I
didn't
see
have
what you're
that
saying. Yeah,
competition,
yeah.
But
it
that's
could be.
not-
But you're going to see that this is it's not just for these hosts. So let me show you more test sets, and you'll see that it's it may be that it's the charge on these hosts, but it's a more general trend. So
if it's a competition, it should be an offset, right?
It should be, which is what he's saying, right?
Yeah, we basically
It's
say
an
offset.
The slope being off. You said the slope didn't improve at all from.
It's a
sorry,
correlation, not the
Or the R square, sorry.
No, it's just the offset is going
Oh,
down,
okay.
right? So the offset's going from -4 to -2.
The slope is still high. What do you think is the reason?
I don't know. Well, I think my guess. Oh, I mean, what do I think is the reason? My guess. There's so many other things that could be improved. We've only made this one very localized change in the water model. Maybe we should be fiddling with the charge. But bottom line is GAF okay? Is AM on, is RESP okay? Right?
The slope has always been large for any charged interaction
Mm.
that we've ever looked at for protein ligand as well, right?
Yeah.
So
So if it
it's
can
really
get
charged, I think it's in general, one of my hunches is that tight binding things tend to like fit really well into the pocket, and they might, for some reason, cause different interactions of like bond stretching or something weird,
It's not modeled well.
or maybe the Leonard-Jones packing is different for that really tight binding situation than a more clinky, binding, loose binding. That's my hunch.
So this is binding enthalpies. Now, this is for most of these cases. There are a couple where we don't have the enthalpies because they're measured by NMR. It's the same host. again, here's experiment, here's the new model, here's TIP3P, here are the other models. And you see again, overall, there's a drop in the tendency to overestimate the heat release in this case, a drop in the RMSE. No real, the correlations aren't very good, but we reduced the amount of bias. And here's some of the other models do better. OPC does pretty well. She goes in the opposite direction. But then going to a slightly different host, this is a close, this should not be highlighted. It's only this one. It's a close relative of this guy, just has some extra methyl groups. There were data for these 6. There's binding free energies and delta H's for some of them. This is experiment, this is a new model, and this is TIP3P for the free energies, and this is the same for the enthalpies. Again, we see a tendency to overestimate the binding free energies and enthalpies less without significant improvement in the scatter. So again, we're decreasing the amount of bias towards overbinding. And finally, this is a set that Neil organized. He has a paper out where he collected this set and did calculations with a number of force fields. This is mostly beta CD, beta cyclodextrin binding various guests. I think a few alphas, a smaller number of
It's a
alphas.
full set.
It's a full set.
It's all 43.
It's 43, yeah. And then some cucurbitural guest interactions. So here you don't have charge.
Mhm.
And we have a mix of binding free energies and enthalpies. So something like 69 guests across these. And I'm just going to give summary data here. So here are the cyclodextrins. This is binding free energy and enthalpy. New model TIP3P, new model TIP3P. So here, less tendency to overestimate in both cases, maybe a little bit less dramatic. And also for the cucurbitural, less tendency to overestimate. No real improvement in the scatter.
It's still a high slope.
It's still, yeah. Especially the cucurbiturals are, yeah.
Yeah, cyclodextrins are loose binders, I would call them. I mean, the magnitude of binding is lower for the affinity, and the slope is more normal, I would think. And cucurbiturals, those are really tight binders, and there's like that really close packing. My theories on that.
Right. So just to wrap up, the total data set is around 120 host guests. Binding data, we see a very consistent pattern. The character and magnitude of the improvement is uniform pretty much across them all. Less overbinding, no improvement in the scatter. And I would argue that this supports the idea of using host guest data to improve at least a water model. It's basically trained on 6 data, and it generalized nicely. So there's more data out there, and maybe Katie will talk now about generating additional.
So this means that we should put improving the water model somewhere on the roadmap too.
Yeah,
But
it seems like it.
does that happen early, or does that happen late, or?
Well, would it break compatibility with, would that be generation 2?
I mean, it could.
Well, I mean, it's independent, I suppose.
So you were changing with sigma and epsilon of this as well.
That's all I was changing.
That's all you were changing. You
I wasn't
kept the
changing the
charges.
geometry. I wasn't changing the charge.
Ah,
It was
okay.
very simplistic.
So, I mean, would we want to have like something that guarantees that proteinaceous interactions with water are also preserved, like hydration or some property that involves?
Do we have mixture data for water with representative groups?
A lot of these are miscible, right? The side chain analogs are not.
Well,
They're oil.
Maybe you've done water models. Do you have a sense on this?
I guess one of my thoughts about building a water model is whether the what should we choose as the foundation, I guess, upon which to build the other parameters. I think it is possible to build a water model where you focus on reproducing the physical properties of water first, and then
Reduce the degeneracy by using something like host gas data. That's,
I think mixture data, even if it's not for the side chain
Yeah.
analogs, but water or alcohol data.
Or
Yeah.
water benzene.
Smirnoff.
Well, benzene and water are immiscible, but they're immiscible at very low quantity. I just keep thinking about, well, I was talking about this with Mike before, and I'm saying, what is it about the host-guest systems, which is sort of showing this new feature of water, and I'm just wondering if it's its organic nature, and so kind of question for the opinion with the water models, if you included mixtures, even kind of concentrated mixtures of miscible organic solvents, along with that, it'd be interesting to see if that would bring about the same effect.
I think that's a really interesting question. I guess I think the results may depend a little bit on the order of operations. I guess maybe I wonder, like, if you were to parameterize water and organic molecules on the same footing using properties of the pure substances, I think it would be very interesting to see how much to see how important the additional information is from the mixture.
I see. But I guess I'm saying if the pure substance of say ethanol, it doesn't see water as the pure substance. And I guess what's emerging here is that when you have the host guest is kind of telling us something about the water model that.
Yeah, I mean, if I could, I want to maybe push a little bit on a point that you can get, plausible water properties from tip 3P, tip 4P, tip 4PEW, OPC. I mean, I would really argue for the degeneracy of using pure water properties or any pure liquid properties and really push for learning as much as we can from mixtures, like has been talked about. I think that otherwise we're just throwing out really useful data.
I think part of the question here though is like, so if we say, yeah, let's make a new water model right away, then the protein force field people will come back or could come back and say, that's great, but you can't use the existing protein force fields. So Liping, do you have an insight? Like, I haven't followed your recent protein force field development work that carefully. Is it tailored to a specific water model? And do we need to, like, if we build a new water model right away, does that mean we break compatibility with protein force fields?
If you change the water model and just and run, say if you run simulations using the same protein force field in 4 different water models, you get differences in the simulation results, which are which I guess border on significant. Like I computed these melting curves of an alpha helix and a beta sheet. These are partially structured peptides,
very weakly stabilized.
Right, and you have to simulate them for a very, very long time to get the melting curves. And then when you change the water model, you can go from say 80% structure to 80% helical content to 40. If you change the water model.
That's a fraction of a k kelp
Yeah, a fraction of a KT.
A fraction of a KT. Yeah, I mean
So-
that's why I like looking at energetics.
Yeah.
So I get
more than conformational preferences.
I guess what I'm sort of saying is that,
Are we going to unfold proteins?
well, yeah, so
We don't
people
wanna do that.
often with current water models sort of treat them as swappable.
Mm-hmm.
But they're also, but this is sort of a rather new approach for a water
Yeah.
model. So I can imagine people coming back and saying, oh, that's fine, but it's not swappable anymore. And I think what you're saying is your data says, well, they're pretty much swappable.
Yeah, I mean the most significant change I found was in these melting curves. Yeah. I think I fully agree with Mike on the importance of using the host guest binding data as a further constraint on improving water models. The only point that I want to bring up is that there's kind of like 2 moving parts in fitting the host guest, right? There's the parameters of the solids, and then the parameters of the solvent. And here we're keeping and here we're using GAF for the solid parameters, and then we're tuning the solvent, and then we're tuning the solvent parameters,
to make it for possible GAF deficiencies.
Oh, absolutely. Yeah, I'm not claiming that this is going to be the right model
Yeah.
for
But
whatever
it,
next
it
gen
might be
is.
better for predictive calculations with GAF. That might be great.
It might be.
So yeah, I agree with that.
Yeah, I mean,
But in terms of the physical properties of water, though, I think the degeneracy is not quite that big. Like in my research, I found that that you can like say tip3p overestimates the diffusion coefficient of water by a factor of 2.5.
Mhm.
If you change the parameters by a few percent, you can reduce that difference in the diffusion coefficient down to about 10%. I can show you a few. I can show you a few figures with like thermodynamic and structural properties if you're interested.
Change by what percent? What were you changing by a few percent?
The tip-free PFB model changes the Lennard-Jones parameters, the charges, and the molecular geometry. So there's a total of 5 parameters.
But
that we
what
change.
kind of percentage you talking about?
So the parameters change by about 5%. There is no parameter that changes by like more than 5%.
Okay.
But you can change the kinetic properties
Right.
by, say like 100 to 200%.
I don't really disagree with you. I'm just gonna sort of push another direction. But I mean, clearly you want the pure water properties to be as good as possible. But I guess if we're trying to support pharmaceutical design, I'd be willing to sacrifice the diffusion coefficient of self-diffusion of water to get the binding right, if that is the trade-off. Now, it may not be the trade-off. Yeah.
Mm-hmm. I think we have the ability to include both kinds of,
Yeah.
of data.
I mean, it would be very interesting to see if we could take, for example, the gradients with something like Smirnoff 99 frost, and then just plug it into every other physical property you've already got in force balance, to use all of the water properties and the host gas properties to. I mean, there might be, here's where the weights come in, right? You have to actually balance them against each other.
Exactly. Yeah, we're pretty close. I mean, so Davis almost has the host gas depth going in Smirnoff, I think.
Mhm.
Great.
So, Katie, you're talking?